All right. Solar cell. Okay. Okay, can you see the slides on the screen? All right. Good. Okay, we'll continue with solar cells. We finished heterojunction yesterday, and you're also going to see that some of the solar cells that we're going to see in this topic are heterojunction as well. Okay. Most of the dominant technologies are homojunction, but we also do have heterojunction solar cell, just like what we saw when we discussed about Panasonic solar cell, the heterojunction intrinsic technology. Okay, so let me walk you through the topic. I'm gonna go from the introduction of the topic, introduction to the solar cell. I'm gonna go through the physics of solar cell by relating to what we've learned last time, particularly when we talk about generation by light absorption, and then the fundamental principle of the solar cell operation. And then I'm going to share with you about photovoltaic technologies as well that we have in the market and also in R&D phase, right? So I'm going to share with you also about PV manufacturing, so that we have worldwide and in Malaysia. Okay, since we are world number 3, okay, let me repeat, we are world number 3 for PV manufacturing as far as the solar panel shipment volume is concerned. So we are world number 3 behind China and Taiwan. By statistics. Okay. So I'm going to show you PV manufacturing and last but not least, emerging technologies in photovoltaics. So those which are still under R&D in particular. Okay. So some of these will also be covered by you in your presentation next week, but I'm just going to go through briefly for those that are related to what you're going to present. Okay. So the major chunk of this topic will be based on crystalline silicon solar cells, since silicon is the workhorse, I would say, workhorse of our semiconductor devices. So do you know this? In a single hour, the amount of power from the sun that we have that strikes the Earth's surface is more than the entire world consumes in a year. So have you ever encountered this phrase, this fact? In 1 hour, the amount of the sun, power from the sun that strikes the Earth's surface is more than the entire world consumes in a year. Only if, okay, there's a condition for that, only if you can harvest 100% of the incident power. So if you can harvest everything from the sun, so the amount of the sun, the amount of power from the sun is actually more than what we need for the entire year. Okay, but unfortunately, the harvesting process, the harvesting activities are limited by the fundamental principle of the technology that we are using in order to harvest the incident power. So we're going to see that shortly, right? So let's look at PV in essence. So let's look at PV in a nutshell. So solar cell, also called photovoltaic cell. So when we talk about photovoltaic cell or PV cell, it's actually referring to a solar cell, right? So PV cell is a solar cell, and what it does is essentially it converts the incident photons or the incident light to electricity, right? So the name of PV cells, we got it from the action of converting the sunlight into electricity. So when we talk about electricity, we're going to expect current and voltage to be the output of the solar cell. So that's why, so we call that as PV effect, right? Photovoltaic effect. So sun coming in or photons coming in, as a result, we got an output voltage, and also the current, and that's why we call it as PV effect. So the first photovoltaic effect was discovered back in 1839. So it's not a really new technology. It was first discovered back in 1839. So if you subtract the current year that we are in to 1839, let me just calculate this, minus 1839, so that's like 182 years back, right? 182 years back, where the effect was first observed, right? First observed by a French scientist called Edmond Becquerel. Okay, so discovered that we can have charges, electrical charges produced in a liquid, right, during the exposure to light. So the first silicon-based technology, first practical solar cell, was first discovered by Bell Labs. Bell Labs in 1954, right? 1954. That was like 20, 60, 70 years ago, right? First practical solar cell with conversion efficiency of 5.4%. 5.4%. Okay, so that's the very first practical solar cell produced. So let's have a look later on at what sort of solar cell did we have back then, right? 1954. So this is how it looks like. If you look at the first practical, first modern solar cell, the conversion efficiency was about 6% back in 1984. So it looks like this, just a very simple p-n junction, if you like, right? So if you look at the first p-n junction, the first paper was published on this back in 1954. You can check it out. The paper was published by Chapin, Fuller, and Person. So the three scientists working on the solar cell back then. So if you look at this device architecture or device configuration, quite a couple of you ask about device configuration. What does it mean? So device configuration essentially means how the device looks like. So how the PN junction looks like. What are the layers involved in the device? What sort of thickness are we using? What sort of doping levels are we using? So what sort of contacts are we using on top or at the bottom, or all the details. So essentially, how does the device look like? So for this particular first practical solar cell, the configuration looks like this. So essentially, it's just an N-type wafer, So the N here is the wafer. Okay, so is encapsulated or diffused with a very thin layer of p-type. Okay, diffused with a very thin layer of p-type. You can see here is wrapped around. So this is the p-type layer. Okay, p-type layer. We normally call this as emitter. So don't worry about this yet. We're going to go through the details later on, but this is just an introduction to the first practical cell. So okay, so as simple as that. So we don't have any contacts in the front. We have everything. We have every contact at the back. So essentially, we have contacts which are in touch with p-type. Sorry, which are in contact with p-type. So this is for p-type. This contact is for p-type, and the center contact is for n-type. Okay, so this is what I said last time. So it's not necessarily you have to have both sides with contacts. Some device configuration or some device architecture also use contacts only on one side to extract the carriers, right? So we'll see why. Later on, and try to make sense of the configuration. So it's a very simple structure, just a planar silicon N-type wafer wrapped with a P-type emitter and a contacted at the backside with P and N contacts. That's it. And it gave us about 5% of conversion or 6% of conversion efficiency like 60, 70 years ago. So the efficiency then grew to 14% in like 4 years' time from 1954. So they did some developments, some improvement to the device. So the conversion efficiency was 14% in 1958. So why PV? So I would like to also relate to to the PV world. Okay, why do we use PV before we go into the device? So first of all, sunlight is abundant. Okay, sunlight is abundant. We have so much sunlight, especially if you talk about Malaysia. Even though we have so much cloud as well, equally, that can scatter the incident photons to multiple directions. But we have so much sunlight available, and will we be what you call out of sunlight anytime? Are we going to be out of sunlight? Except nighttime. Nighttime, of course, there's no sunlight. But will there be another sunlight tomorrow? Should be yes, right? Should be yes. Okay. Kalau tak ada sunlight, then something's wrong with the world. And we are approaching uh, the doomsday already. Okay. Kalau matahari tak ada, then something's wrong already. Right? Else, sunlight will just be abundantly available to us. So it's a form of a clean energy source, and the solar cells get more efficient over time. We'll see later on. And then we have consistent reduction in technology costs as well due to higher and higher volume of solar cell production worldwide. Okay, so that will drive down the cost. So when you talk about solar technology, we are talking about USD per watt as our technology cost benchmark. Okay, USD per watt. This is called technology cost, tech cost. So this, in a nutshell, means that how much you spend in order to fabricate the cell and the panel or the module. When I say module, it's referring to panel, panel besar, which includes 60 or 72 or 96 cells altogether as one plate, right? So how much do you spend to fabricate the cells over how much power can you extract? Okay, how much power can you extract from this panel? So it's called technology cost benchmark. Okay, so we'll see how does this technology cost benchmark evolved since 1954. So when you want to measure the conversion efficiency of a solar cell, we will need to use a standard illumination setup. Okay, and this standard illumination setup is called standard test condition, or STC. Right, STC means you need to use a solar spectrum with AM 1.5, so which takes this shape. So to be more specific, we're going to use AM 1.5 G. G is global. You can also have diffuse only, right? You can also have this is the standard that we use in order to compare or to claim your efficiency is the highest one or the best one. You cannot simply use any illumination spectrum, right? Because you want to be the same in using a source in order to know your output in comparison to other people's cells. So this essentially consists of AM 1.5 solar spectrum, illumination level 1000 watt per meter square. It cannot be lower than that, else it will not be called as STC. And the temperature has to be controlled at 25 degrees C. So these three conditions, right, will make the STC, standard test condition. Okay, so we know that our sunlight consists of UV photons and visible photons and also infrared photons. Okay, so this is essentially what AM 1.5 looks like. And we use AM 1.5G for any solar cell that you want to use on Earth. Okay, on Earth, for Earth application. If you're talking about Earth, also means a terrestrial application. We call it as terrestrial application. Terrestrial. Okay. So if you want to use the solar cell for space application, you need to use AM0. Okay. This is for extraterrestrial. Extra itu maksudnya kat luar, kat space. Kalau nak pakai on satellite, then you have to use AM 1.0 standard in order to qualify your solar cell. Okay, for example, if you want to send gallium arsenide on certain satellites, that'll be outside for a couple of years, for example, then you have to use AM 1.0 to to measure your electrical outputs from the cell. Okay, so if you cut a solar cell, so say this is your solar cell from the side, and then if you cut the cross section, so this is what you get. So from the front to the back, okay? The front ke atas, so say that your sunlight is shining this way from the top. So if you cut the solar cell, this is how it looks like. It is composed of a couple of layers. So the top here is the contact, metal contact. So it's labeled there already, front side grid. And we've also seen this in our yesterday's lecture. Tab and metal fingers, the small one are called fingers, right? And the tab. And then this is to extract the carriers on both sides. So you also have contacts at the back, right? Contacts at the back. So this is the rear contact. So the front one typically uses silver. The rear one usually uses aluminium. So for the time being in mass production, okay? So on the top layer, you have silicon nitride anti-deflection coating, okay? So some of you might be familiar with this. Silicon nitride ARC, we call it ARC, anti-reflective coating. So the job here to reduce reflection, to reduce the front reflection from the silicon, okay? Then followed by an N plus emitter. Okay, N plus emitter is this, the red layer, okay, N plus. So typically the doping level is somewhere 5 times 19 per centimeter cube. N type, okay, N plus. And then followed by P-type silicon. So the whole bulk here is the P-type silicon, the gray color. So typically the mass production doping level is about 1E16. So you're going to see why 1E16, more or less. Okay, so that is equal to 1 ohm cm. So we've seen yesterday, or not yesterday, last time, when we talk about the resistivity versus doping level curve, right? So we discussed about if you're given wafer of 1 ohm cm, so what's the corresponding doping level in the wafer? And that's about 1.5 E16 for 1 ohm cm. So we also have at the back local BSF layer. So don't worry about it yet. So it's called back surface field, aluminum back surface field. So it's really unique to this device, back surface field. What is it doing? So the role is to minimize rear recombination in the device. Okay, minimize rear recombination in the device. How? We're going to see later on. And then we're going to have some dielectric layer as well, typically at the back, okay, here in between, you're going to have a silicon dioxide, passivation, okay, and then rear contact. So that's how a device configuration, if like, device configuration for this case looks like, right? So more or less you have like 7 layers or so, 1, 2, 3, 4, 5, 6, yeah, 6 or 7 different things in the solar cell, okay? So a solar cell is a p-n junction device, as we discussed last time. So you can relate this with the N plus emitter, the very thin layer on top, and then the p-type wafer. So that forms the p-n plus junction, okay, which is essentially a p-n junction. So we've discussed some of this last time. In order for us to use a solar cell, 4 things need to happen, okay? The first one is absorption of the incident photons, or incident light, where the photon energy has to be more than or equal to, okay, more than or equal to the band gap. So in this case, the incident photons have to have energy of more than or equal to 1.12 electron volts in order to excite valence electrons in the crystalline silicon in the valence band into the conduction band for conduction, right? And then upon the light absorption, we're going to generate electron hole pairs. Okay, electrons are going to be excited into the CB, and holes are going to be maintained in the VB, right? And then upon the generation, the moment you've got your electron hole pair, the electrons and holes need to be separated. Remember last time we discussed about generation of excess carriers and then the role of electric field to pull one carrier type to one side and another carrier to the other side. So in this case, the separation will be carried out by the p-n junctions electric field, where, so let's assume that the base or the wafer is p-type and the emitter is n-type. So in this case, the electron will be collected at a junction in n-type, and hole is already in the p-type. So if you generate somewhere in the depletion region, for example, then electrons are going into n-type and holes are going to p-type. So electrons eventually will be collected by the front contact here. Holes are going to be collected by the rear contact here, okay, in order to complete the circuit, right? In order to complete the circuit, the external load. So yeah, therefore the collection of carriers in the metal contact, okay, so they need to be collected by the contact. So you can see here in the second illustration down there where electrons are going to the right, holes are going to the left, okay. So then they are collected and complete the circuit. So those are the 4 steps that need to take place in order to make sure that the solar cell is functioning. So we've also discussed about this collection probability, where the surface preservation is super important when we talk about the solar cell. So that means, this essentially means that the front surface here and the rear surface there need to be properly preservated, okay, in order to ensure that your collection, the carriers are high on both sides. Okay, we've discussed this one. I don't want to go into the details again, right? So okay, this is another way to illustrate the collection probability, or we call it a quantum efficiency. QE, what it means is how many electrons are collected, number of collected electrons over number of incident photons. Quantum efficiency. So that means if you have a QE of 100%, so that means for every photon incident on this solar cell, for every photon, 1 electron hole pair will be successfully collected. So 1 to 1. So that is the ideal of the quantum efficiency case, right? So most of the time we will have a curve of less than 100%. So we normally have something like this, right? Something like what is already shown there. So ideally you want to have a square collection probability, square shape collection probability, where it is 100% collected. So 1 here means 100%, but in the real cells, this is the typical EQE, external quantum efficiency curve, that we normally see even in mass production. So we have discussed last time when we talk about photons, UV photons. Remember the UV photons, visible photons, infrared photons. Still can recall this? Where do we generate, where do we collect where do we absorb the UV photons? Anyone? Let's recall what we learned in generation last time. Where do we absorb the UV photons? In the silicon? Kat mana? You can see that throughout the thickness of the silicon. So where do we collect the where do we absorb the UV photons? Come on, someone. Yeah, bang, yeah, but where do we collect? Throughout this silicon. So this is the whole silicon thickness. The question is, where do we collect? Where do we absorb the UV photons? In the silicon. Kat mana kita absorb dia? Kat mana? Which one is the UV photons? Surface, right? So UV photons are absorbed at the surface because UV photon has the highest energy. Okay, so UV photons will be absorbed here. So visible photons will be absorbed somewhere in the bulk, dekat tengah tu. IR photons will be absorbed at the back if your thickness is enough. Remember last time we discussed about the sponge thing, sponge and water, kan? Lagi banyak volume, then the more you can absorb. So when you want to see this quantum efficiency curve as on the solar cell, so it reflects the very same thing. Okay, it reflects the very same thing. How? So let me see. Let me show you. You tengok dekat QE curve sekarang. So you can divide the QE curve into 3 different wavelength regions as well. Okay, you can divide into, say, UV region, and then you can divide into visible region and also IR region. Say this one is UV, say this one is visible, say this one is IR. Okay, so if you see this curve, it actually reflects the collection of carriers. Remember how many electron hole pairs are collected? Okay, collection. Collection. The keyword is here is about collection, carrier collection. So whatever the probability of collection in the device which comes from the front surface will be reflected in this region, in the solar cell. Maksudnya you tengok solar cell tu macam ni. Katalah ni, this is the thickness of the solar cell. So this is your silicon cell, for example. So whatever you collect, whatever carriers that you collect from the front side of the surface, front side of the solar cell will be reflected in the UV region. Yang ni engineer dekat company solar pun tak tahu. Okay. So hari tu dia ada isu, dia pernah tanya saya. Dia tak tahu that this is the correlation of the solar cell performance. Okay. So now you learn this already. So that means if you see any low curve or high curve in the UV region, so it shows what is happening on the front side of the solar cell. So it has nothing to do with the rear side of the solar cell. Okay, just the front side. Okay, if you go slightly deeper into the bark, so whatever happening in the bark will be reflected on this curve in this region, in the visible region. Okay, so if you see you get low curve, for example, katalah you punya curve macam ni, high, then you suddenly get it like that. For example, your curve is very low in the visible, so most likely the inside of the volume has some problem with it. Okay, maknanya ada portion dekat tengah ni of the silicon cell yang ada problem that you have to check. Okay, nanti you will see this if you go to internship in any solar company like JA or Jinko or First Solar, or you get to be a process engineer or R&D engineer, you'll see this, you'll encounter this. Okay, so the same goes to the back as well. So anything you see on the back, at the back of this curve in the IR region, is reflecting what is happening at the rear side of the cell. Okay, apa yang jadi kat belakang ni is actually reflected in the UV, in the IR regions. It has nothing to do with the front region. Okay, so this is what I call one of the important knowledge that you have to know if you want to go into solar cell industry or you want to do solar cell research or something, right? So the QE curve, the wavelength reflects the location in the device, right? So the UV region reflects the front side, the visible region reflects the middle of the wafer, the middle of the solar cell, and the IR reflects the rear side. Okay, clear? So this is the diode curve, diode IV curve that we discussed last time. The J naught component, okay, the exponential component, the ideality factor, the KT, QV, and everything, and then the load current produced by the solar cell. Okay, IL here is the load current produced by the solar cell, right? So this is the equivalent circuit. You can also see this on PV CD-ROM, right? So this is the curve that you're gonna see from a solar cell measurement. So we're gonna go deeper into later on. This is the I, this is V or J versus V, if you like. So essentially you'll see like that, right? So when you see this curve, the intersection between the curve to the y-axis is called short circuit current density, JSC or IC. Some use IC, some use JSC, depending on the context of measurement. The intersection between the curve to the x-axis is called open circuit voltage, right? Open circuit voltage. So JSC means when the solar cell is short-circuited, we've discussed last time during PN junction. So that is the amount of current that you will get at 0 voltage. Okay, 0 voltage, you're going to get that current. And then when you leave the solar cell open circuited, so that means the current is 0, you're going to get the VOC. The voltage measured across the solar cell when the current is 0. Okay, so that's what they mean, JSC and VOC. So that is the short circuit current. So this is open circuit voltage. And then when you multiply the current and voltage, apa kita akan dapat? When you multiply I and V, what do we get? From your previous knowledge, if you multiply, yep, P, right? P equals to IV. P equals to IV. So power equals to current times voltage. So if you look at this curve, for example, this curve or that curve, if you see this, let us move from 0 to VOC and try to see what do we get. So at 0, at the origin, we have what? What is the voltage? The current is IC. At this point, at the origin, the current is IC and the voltage is 0. Therefore, IC times 0 equals 0. So you have 0 power from the solar cell. Okay. On the other hand, if you go to another extreme where your VOC has a value, but your current is now 0. So I times V, VOC times 0 is 0. So you get two zeros on the left and on the right, respectively. So in the meantime, in between, when you go to the right, you have values of both, right? You have some current, you have some voltage at the same time. So therefore, you're going to get some magnitude of P. So you're going to get increasing power until this point. Okay, and this is the point where the solar cell is going to generate maximum power. We call it P max at that point, where the current is maximum and times the voltage that is maximum. So I max times V max equals to P max. So that's why you're going to get this PV curve. This PV curve means power against voltage curve. We call that as PV curve. This one, PV curve. Yang macam ini is IV curve. So from IV curve, you can derive your PV curve, right? So another important factor that you can see on this curve is called a field factor. FF, field factor. Field factor is actually, if you look at this curve, it measures the squareness of the curve. Okay, the squareness of the curve. How square is the curve? You want to be as square as possible. Okay, you want to get this ideal square curve, right? So the proportion of the squareness of this curve from the cell over the ideal square curve is called field factor. And that is given by I max times V max over ISC times VOC, right? So I max times V max over ISC times VOC. And that will give you field factor. So the field factor normally appears as 80% or 70% depending on the quality of the cell. So I think the world record cell now has over 80% of field factor. Okay, so we're going to see later on as well. So this is the equation again, right? In order for you to evaluate the conversion efficiency, so we normally talk about the efficiency of the cell. Okay, efficiency of the cell. So that is given by P out over P in, right? P out over P in. So the basic efficiency calculation of machine, for example, P out over P in. And your P out is given by VOC times ISC times field factor. P out over P in. How much is the P in? P in is the incident light at STC, standard test condition, which is equals to 1000 watt per meter square, or also equal to, if you change this to milliwatt per cm squared, it's going to give you milliwatt per cm squared, but 100 cm squared, 100 milliwatt per cm squared. So they are both equal. So you can mention either your STC is at 1000 watt per meter square or 100 milliwatt per cm squared. Okay. So at 25 degrees C, obviously, and using AM 1.5 G solar spectrum, STC. Okay, STC. Standard test condition that we just gone through a couple pages back. So that's how you calculate your conversion efficiency of the solar cell. So if you know the VOC, if you know the IC, then yeah, you can calculate the fill factor from the IC, VOC, IMAX, PMAX, and then you know the P in at STC, then you can calculate the efficiency of the cell. You can just times this one to 100% in order to get 20% or 30% or 15% or whatever percent. Okay. So this is a chart of technology generations. Okay. So we have altogether 3 generations of PV technologies. So this from UNSW. So the first gen, so we call it by generation 1, generation 2, generation 3, but we also say first gen, second gen, third gen. Okay. If you are in the field of PV, then that's how people in the field say it, right? First gen, second gen, third gen. Right. If you're saying, if you're talking about first gen, then we are talking about solar cells that are based on crystalline silicon wafers. Okay. So they're called wafer-based crystalline silicon solar cells. So this first gen is what dominates more than 90% of our market now. So if you see on the roof, you'll see these panels. If you see in the solar power plant, you will see these panels. If you see on the facade on the front of the building, most likely you'll see this panel as well. So it dominates more than 90% of the PV industry and also the market. So back then, so this chart was like before when I did my master's. So I think at least 10 years ago. So the green color refers to the first gen, the yellow color refers to second gen, and red color refers to the third gen. Okay, so let's look at the second gen and third gen first before we look at the chart. The second gen is related to thin film solar cells, right? Thin film solar cells. For example, if you talk about cadmium telluride, okay, some of you have to present on this, or CIGS, or we call it as 6 solar cells. CIGS, we just say 6, and then amorphous silicon, perhaps amorphous silicon solar cell. So they are called second generation solar cells. So the difference between the first gen and second gen is in the thickness of the device. So the first gen solar cells use a thickness of about 160 to 200 micron. 200 microns. So that's about twice our hair thickness, if you like. So back then, 10 years ago or more than that, the technology cost for the first generation was so high. It's like $2-3 per watt. That's the technology cost of the first gen. So back then, when the technology cost of the first gen was so high, if you can look at this, on the efficiency and cost curve, the first gen was like between $1 to $3 per watt back then. Okay, so this is like before 20, so at least 10 years ago. 10 years ago. Chani, 10 years ago. So back then, the cost of first gen was like $1 to $3 per watt. So that was so expensive. And that's why scientists came out with second gen technology where we can reduce the thickness of the device to less than 5 micron. So just look at the thickness difference now. We are reducing the thickness from 200 micron to only 5 micron. Okay, so that's like what, 40x 40x reduction in the material consumption that you have to use in order to fabricate the device. So reducing the material consumption in the cell will reduce the cost as well, because remember the dollar per watt. So lesser material means less dollar. So dollar per watt, if you can extract the same power, for example, then your dollar per watt will reduce. So that will bring down the cost of the second gen technology slightly to the left. But the problem is, back then, the conversion efficiency of the first gen was somewhere here, about 20% or so for the first gen. But for the second generation, the efficiency is like 5 to 10% lower. So say it's about 10% conversion efficiency. So lower thickness will result in lower efficiency of the device. Okay. Then as a result, people think, okay, why not we came out with third generation then? We have to use the very same amount of material. So that means on the cost curve, on the x-axis, you are still there, cost dollar per meter squared, for example, same amount of material, but push the conversion efficiency a lot higher by, say, another 10 to 20%. So that will give you the third generation solar cells, so which is called high efficiency, but based on thin film solar cells. So they're based on similar amount of materials, or in fact lower, but the efficiency is like 10% higher at least. Okay, so this is the history of first gen, second gen, and third gen. So we still call them so as first gen, second gen, and third gen now, right? So now we'll see, I'll show you later on that the cost of this first gen, has dropped tremendously in the last few years, in the last 7 to 10 years or so. I remember last time when I was doing my MSc back in 2009, the cost was like $2 to $3 per watt, and now the cost of this first gen technology has dropped tremendously. Any guess what's the current cost? So it was like $2 to $3 per watt in 10 years ago, in 2010, about 2010, 2011. So now the cost has gone down to, any guess? Siapa nak teka? $1, okay, juara say $1. Any other guess? Let's have 3 guesses. $1, $3. $3 makin mahal ke? So it's gone down already. So it was like 1 to 10 sen, 10 sen, okay. 10 sen already, less than $1. Okay, the cost has gone down to RM1. Well, that's pretty close if you convert. The cost has gone down to 20 cents per watt. Sekarang, as of 2020, in the latest report, if you are in my group, then you know. I shared this morning. It's about 20 cents only. So one order of magnitude lower than last 10 years. So $2 per watt down to 20 cents per watt. So that means the technology is getting more and more affordable. So that's why you get to see more and more solar farms being commissioned in Malaysia, and you get to see more and more solar being installed on rooftops. And we have more aggressive policy at government level in order to encourage people to install more and more solar, right? So this is what is the current situation. And I'll explain later on why is it so. Why is it getting so cheap? So, right, first generation, and let's go on for another 5 minutes or so. First gen and second gen are now in heavy mass production. Okay, so remember the first gen, this mono and poly are called first gen, and they are together, they dominate more than 90% of our current market. And the thin film technologies like amorphous silicon, cadmium telluride, SiC, and the rest has only less than 10% share in the market. Okay, thin film technology. So the third gen, on the other hand, some of them are already in mass production, but very small volume, perhaps less than 5% or so, and most of them are still in R&D. We're going to go through this one at the end of this topic, okay? So first gen, how do they look like? So first generation consists of mono and multi. So we've discussed already about mono and multi. Remember, what can you see from this mono and multi, the difference? What is the obvious difference from these two wafers? Let's recap on what you've learned in the very first topic for this course. What is the obvious difference that you can see? Anyone? So obvious, right? Apa beza dia? Pattern surface. Okay, you say pattern surface. Okay, any other answers? Color is not uniform. Okay, good. Color is not uniform. Any other answers? What else is obvious? What is obvious? You can see different colors, right? So why different colors? Anyone? Why is it different? Why is it dark blue, navy blue? Ah, yeah, light blue, many crystals, right? So the reason is due to the presence of many crystals, different grain orientations, different grains. You have grains there. Do we have grains on mono? On the other hand, do you have grains? How many grains do we have in monocrystalline? One grain, yeah, single grain, single grain. You only have single, mono. That's why we call it as single crystal or single grain or mono. Satu lah mono kan. Multi means more than one. So that means you have more than one grains that are responsible for the different reflection levels. So that's why some regions look navy blue, some even darker, some so light, some a bit close to white perhaps. So they are different grains. So that's why we call them as multicrystal. Okay, multicrystalline. So monocrystalline, single grain, multicrystalline, more than one crystal separated by grain boundaries. You can recap this in assignment 1. We did discuss about the definition of mono, poly, or multi, if you like. Mono and multi ni macam poly sama. Sama monopoly and amorphous as well. So both use wafer thickness of 180 micron. Okay. Now mass production, I think if you talk about JA solar, they're using 165 to 175 micron in Penang, pass. So efficiency ranges from 18 to 25, reliability guaranteed for 25 years. So very stable technology, a very stable technology. It lasts for 25 years in the field, with fluctuating temperature, humidity, storms, sand, and many others. Okay, 25 years. So this is first gen technology. So how about second gen? So second gen are based on thin film solar cells deposited on foreign substrate like glass, plastic. You can even consider fabric, baju, kain, langsir, jacket, whatever, fabric, selimut ke, kemah, tent, right? So whenever basically they are not rigid surfaces. You can bend, you can lipat, whatever, you can fold. So you can see here, you can bend this, you can fold. This one is curvy as well, so you can apply to curvy surfaces. Where you can't, if you use this, if you use first gen, you can't. You can apply this on bendy surfaces or curvy surfaces. You can only apply on rigid surfaces. Okay. On the other hand, if you use a second gen, you can use on any curvy surfaces or kain, jacket, stuff like that. So since the thickness of the device is very thick, so most of them are less than 5 micron. So they are very, very fragile in nature. 5 micron, you just imagine you take your hair 100 micron, say, thickness, and then you slice your hair thickness by 20 slices. Potong 20, you punya rambut tu. So that's going to give you 5 micron thickness, okay? So therefore, when it is so thick, it's so thin, it'll be so fragile. So bila dia fragile, you cannot use it on its own. It has to be sitting on a supporting substrate, which can either be glass or plastic or something else, that are thicker in nature. They can support the device. So these foreign substrates like glass or plastic or some other stuff will give the device some mechanical strength, okay, for practical application. Mechanical strength of the device. So nak lapik dia, you ada ni, then it's very brittle and fragile, so you have to put on something that is strong. So that will make the whole system stronger. But the current generation, the light absorption is only done by this 5 micron material on the glass or on the plastic, right? So it's like 150 to 204 reduction in the thickness, therefore reduce material consumption, therefore reduce the US dollars needed in the technology cost. However, the efficiency is only 10 to 15%. Okay, when the cost of the monocrystalline and multicrystalline silicon, the first gen, was so expensive 10 years ago, thin films have been said, it was said last time that thin films are going to overtake the market. So maksudnya thin film akan dominate and then crystalline silicon will be out of business in like 5 to 10 years. But it's showing the opposite trend now. So since the cost of the mono or the first gen has reduced tremendously, sekarang banyak company, most of the companies which are based on the second gen just cannot survive the business, right? So you see in the Europe, in the US, in fact, worldwide, many companies that are based on second gen have filed for insolvency. Okay, insolvency. Apa insolvency? Apa nama aja? Insolvency. Bankrupt lah, bankrupt. File for insolvency, bankrupt. So they went bankrupt. We can't even see it then. What do you mean by that, Juaria? Because it's so thin, is it? Okay. Yes, of course you can't see because it's like 5 micron or less. By the thickness, by the cross section, you can't see but if you put on the front side, obviously you can see. Okay, but it's so thin from the cross section. So examples are amorphous silicon cadmium telluride 6 ZAT386. ZAT386 is a compound solar cell based on copper, zinc, tin, sulfide. Okay, copper, zinc, tin, sulfide. If you talk about CIGS, it's based on copper, indium, gallium, selenide. Okay, so CDTE is cadmium telluride. So it can be compound as well. It can also be elementary in nature. So let's finish off with this third gen, and then we'll continue tomorrow with the rest. So the third gen, on the other hand, is a new technology using the very same thickness of the device, but capable of higher conversion efficiency. So the examples of the third gen are organic solar cells, and perovskite solar cells. Okay, organic solar cells have been around for quite some time, and the conversion efficiency, if I'm not mistaken, is somewhere up to 15% or so. On the other hand, perovskite solar cell is a new kid on the block, right? A new kid on the block. Back in 2009, if I'm not mistaken, 2009, the conversion efficiency of the perovskite is only about 3.8%. And as of 2020, now, the conversion efficiency is already beyond 25%. So fast. If you look at the learning curve, the gradient of improvement for perovskite is like in 10 years, it's gone up by 22%. Absolute, right? The thickness is about 300 to 500 nanometer. It's even thinner than the second generation. So if you talk about 5 microns for this, less than 5, and we're only talking about 300 to 500 nanometer for the third generation. So it's even thinner. Small market. So for organic small market, for perovskite, we just have few companies worldwide that have just started their pilot line production and even the real production line. I'm going to show you later on. So perovskite is a new emerging technology. Now it's about 25% by latest conversion efficiency record. As a single junction, as a single PN junction, perovskite alone can give you about 25% world record cell, right? However, there's always a but, okay? However, these technologies, perovskite and organic, they suffer from stability issue. So if you compare with the first gen just now, they can last for like 25 years in the field. So in order for other technologies to beat the current technology, which is based on the first gen, so they also have to have comparable stability guarantee, right? However, this is not as stable if you compare to crystalline silicon technology, the first gen. However, this is still under intensive research. So people are doing many different things, many different approaches in order to study what is causing the degradation problem in the perovskite and in organic solar cells as well, and try to address accordingly so that the stability can be improved over time, and eventually it can be even comparable to crystalline silicon solar cell, who knows. But at the moment, there's no way that the current technology in the third generation can be comparable in terms of stability to the first generation technologies. Okay, so I'm just going to stop here. We're going to look into the annual production and what sort of materials we use, and then relating to the previous fundamentals that you learned in generation and recombination last time. Okay, so any questions at the moment? All right, one question there. Okay, group presentation. Okay, group presentation. There's a certain companies related to the semiconductor we assigned to. How do we insert this point? Well, you can just add on one slide, for example, and say if we are doing a cadmium telluride, so it's related to First Solar, then just mention on one slide that the company related to the device is First Solar, for example, and you can also include some other companies if you want to, and just explain a little bit that what First Solar is doing, what sort of technologies are they doing, what sort of conversion efficiency, and how the panel looks like produced by First Solar, stuff like that on one page. Is it okay, Cornelia? Right, cool. So yeah, if you do well, JFET or CMOS, or well, no CMOS, right? Organic solar cells, just try to find for yourself what are the examples of companies that are responsible for the manufacturing of the devices. If you can find those in Malaysia, then include. If you don't find anything in Malaysia, any company in Malaysia, then just use any companies outside there, right? Cool. Any other questions? So far okay with the solar cells. Anything you couldn't follow, or so far so good with solar cells? So far so good. Then we are now on page. Let me have a look again. So we're now about 20 plus. So I might need about 3 classes for this. So if that's the case, then it's gonna be tomorrow and Monday perhaps. Yep. So we'll probably finish on Monday. Test dua ada calculation tak? I will let you know. Right? Kalau ada calculation, there'll be a little bit of calculations. So remind me, Monday public holiday? Really? Betul ke? Public holiday apa? Oh, okay. Public holiday then. Alright. Terlupa lagi. So, yeah, I'll finish on Tuesday, then our presentation will start on Wednesday. Sorry, saya terlupa. So, yeah, okay, finish off Tuesday, presentation Wednesday then. 7 hari bulan ke? So let's look at it. I forgot already. So now it's 2nd. 7 is Monday. Okay then. So 7 lah, huh? First, yeah. Okay. So Wednesday is the first presentation. I believe this solar cell slide has about 60 slides altogether. I think I'll probably go through another 20 plus tomorrow, and then Friday not at the class. Then Isnin cuti. Selasa I'll finish off solar cells. Then Wednesday then for the first presentation. First group, First group and second group we'll do on Wednesday. Then third group and fourth group we'll do on Thursday. Okay. Then another remaining groups will proceed week, okay, Monday, Tuesday, right? So I think we can finish off everything by week 14. I think so. Yeah. All right then. Any other question? Last one. No more. All good. Okay. Thank you for the reminder on the akun saya ni. Saya pun tak ingat. Tak follow sangat. Right. Bye bye. Take care. Assalamualaikum.